Welcome to the Real Curriculum. Another application of components of vectors is in alternating currents. So, first of all, you learned about the electric circuit, the simple electric circuit, the direct current electric circuit. You have your voltage source, then your resistance, then your current flowing to the circuit. So this is your V, your voltage source, the current that flows in the circuit, then the resistance, a simple direct current circuit. Then you have from Ohm's law that the voltage is equal to the current times the resistance. Right. Then now, as opposed to your alternating current circuit. So the alternating current circuit has voltage source, then it has three major components. You have your capacitor, your inductor, and resistor. So you label them this: resistor, inductor, capacitor. Then your current flowing to the circuit. So the idea is that in an alternating current, one of these two components should be involved. That's what makes it an alternating current circuit. Once it's losing this and this, it looks like this. It's a direct current circuit instead. So it might have all this, or it might have just this with one of these two. Just a capacitor, or just an inductor, or both. So in this case, your voltage is equal to the current times this term. So this is the effective resistance. Just like your voltage equals to your current times the resistance here. This is voltage equals to current times this effective resistance in the alternating current circuit. So the components of this effective resistance is or are your resistance itself, your inductive reactance, and your capacitive reactance. So these reactances are each the resistance that result from the inductor and the capacitor respectively. So that's the term for it. So if it was just a capacitor in this circuit, no inductor, then the XL will be out. You just have only the XC. So by the time you square, this minus goes, so you just have R squared plus XC squared under this square root sign. If it's only the inductor here and no capacitor, you just have R squared plus XL squared under the square root sign. So as simple as that. So now, this effective reactance, that's how it's mainly called, is called the impedance. So now the main aim to relate to this our component of vectors we're talking about is the impedance. Just compare this impedance relationship. Just look at it closely. What does it look like? By the time you square both sides, you have this. Does it draw anything to your mind? This is Pythagoras' theorem, one of the peculiarities of a right angle triangle. This is a right angle triangle. Then this should be the hypotenuse. Then this and this, R and XL minus XC, would be either of these two places. So let's look at this deeply. Alright, watch this. You should be familiar with this, that your power consumed is equal to cos this. This is one of the relationships you come across in alternating current circuits. You know that power from a direct current circuit is equal to current times voltage in the circuit. But in the alternating current circuit, you have this. This is called phase angle. The idea of phase angle is due to the fact that the current and the voltage in an alternating current circuit are out of phase. You know that in the direct current circuit, comparing your voltage and your current with time, you just have constant, a constant graph, constant values, because it doesn't fluctuate. The voltage is the voltage, the current is the current, as far as the direct current source. The direct current circuit voltage source is still performing at its original value, and you have constant values for the voltage and current. So this could be the voltage, this could be the current, any of these two graphs, depending on which one is higher. You have this constant. Compared to the alternating current situation, you have something like this. So because of the alternating current situation, it's a periodic function kind of situation, the graph. You'll notice that the values, first of all, the values are fluctuating. Then the time it will take the voltage to attain zero, or the current, because any of this could be the current or the voltage. So the time it will take the voltage to reach this zero mark is different from the time to take the other one to reach the zero mark. So at some time, something, this one got to zero here, but at some time, something, this one had already, at some earlier time, this one had already reached that zero mark. And because at the point this one, anything this one is, any of V or I that this one is, any of V or I that this one is, by the time it gets to zero, the other one is already at some positive value. It's already at some higher than zero positive value. So it means that one had already attained zero at some earlier point of time. So that's the out of phase idea. So the extent of time from here to here will give you this out of phase value that you call the phase difference, but not just time. When you multiply the time by the angular velocity of this periodic function, when you now have the angular velocity times time in that axis, it will be equal to the angular displacement, which the phase angle is a component of. So this portion represents this phase angle. So that's just the idea of that, where the phase angle came from. So it's just pointing to the fact that the voltage and the current are out of phase, unlike the direct current situation where they are in phase. The time it will take the voltage to attain zero is the time to take the current to attain zero too. So that's the basic understanding of where this phase difference, the phase angle came from. So now you have this is the phase angle. Then now you know that if you compare this to the direct current situation, the power consumed is equal to the current times the voltage. The current times voltage. So if the power consumed is equal to the current times voltage, okay, let me put it here, comparing with the direct current situation, P is equal to IV. So this will be equal to I squared R. Yeah, because V is equal to IR. So by the time you substitute IR for V here, you have I squared R as your P. So V in the alternating current circuit, V is equal to IZ. So P here will be I squared Z cos phi. The power consumed will be I squared Z cos phi. So and we know that if you compare this to this, compare these two P's, they are both power consumed. It means that R, since P is equal to I square Z cos phi, P is equal to I square R, then R should be equal to Z cos phi for power consumed. So cos phi will be equal to R over Z. So from our trigonometric ratios, SOHCAHTOA, cos of an angle is equal to the adjacent to the angle divided by the hypotenuse. So if we come back to this right angle triangle here, if we place our phi here in this right angle triangle, then the adjacent to it should be our resistance, meaning that the opposite would be this other one, because we've already established that these two components should be one of these two sides. Each of them should be each one of these two sides of this right angle triangle. So since we've established that R is the adjacent, then XL XL minus XC should be the opposite. Simple. So we've figured this out. Then now, understanding this right angle triangle, we can do the same thing here. You know, we already have one here. The component R is equal to Z cos phi. So it is the, based on the phase angle, the phase difference, R is the cos component of the impedance. Definitely this total reactance, or this inductive and capacitive reactance, yeah, we can call it total reactance, since the impedance is the total resistance, and this should be the total reactance. Anyways, this is the sine component of Z. Simple. So we have our components for the resistance. Then now something else. The power. We have the power consumed, which we've already shown here. The power consumed is IV cos phi. The power that was supposed to come, the apparent power that was supposed to be the power of the circuit if it were not alternating current circuit, is IV, that we already know from our direct current situation. Then it means that the other component of power will be IV sine phi. So this is the amount of power that would have been actualized, that would have been obtained if the energy that was stored wasn't stored. So some energy was stored. You know, the energy, the consumption of energy is what results to power. So since some amount of energy was not consumed to give you power, instead it was stored, that portion of the energy is what should have given rise to this power here. So this is the power stored, if you have to call it stored power. This is the power, amount of power that was stored as energy. So this is the amount of power that would have been gotten from the energy that was stored. So that's this. So we have our energy the power consumed, our apparent power, the total power that is supposed to be actualized if it were not alternating current, apparent power. Then we have our power from energy stored. So all these things too can fall into a right angle triangle situation based on the phase difference. So we know that the P IV, let's call this PC, P consumed, and this is P stored. So our main P equal to IV. Our P consumed, PC is this. Our apparent P, which should have been the total P if it were a direct current circuit, IV is this, and this is the P stored from the energy stored. So the power, the apparent power is our hypotenuse to this right angle triangle. Then our power consumed should be the one related to the voltage, to the resistance. Is the one related to the resistance, because it's the resistance that consumes the power while the other component stores the power. So it will take the adjacent position of the resistance too in this power situation. Even from its relationship, you know, it has to be, since it's the cos component, it has to be the adjacent to the angle. So PC is here, then PS is there. So we have this and this from the application of components of vectors in alternating current circuits. One thing that I didn't mention before that will help you here is the idea that the inductor helps the voltage to lead the current. So that phase angle thing we showed on that graph, the voltage will be the one that arrives at the zero before the current. Then when a capacitor is there, it helps the current to lead the voltage. So in the case of inductor, the voltage leads and the current lags. In case of capacitor, the voltage lags and the current leads. But in a situation where you have both of them in the circuit, depending on their value, the voltage might lead or the voltage might lag, the current might lead or it might lag, depending on the values of the capacitance and the inductance. So this is a pure inductive alternating current circuit. So the voltage will lead. So the voltage leading would mean that the vector diagram will be such a way that, okay, if you look at the options, you see that the voltage is given in two aspects: the voltage across the inductor and the voltage across the resistance and the resistor. So definitely the voltage across the resistor and the voltage and the current are supposed to be in line, because if you look at the direct current situation, that's what you should have. The resistance and the current are supposed to be in phase, they're supposed to be in line. So that one is the first thing you pick out from here. Then the other thing you pick out is that the voltage leads the current in this situation. So since the voltage leads the current, the voltage, the vector diagram should be having the voltage that leads up. The voltage that leads will be up and the current will be down. The idea is that when you lead, you're up. It means that, okay, it's just as if you're drawing them anti-clockwise, as if they are rotating anti-clockwise. So if they are rotating anti-clockwise, the one that leads should be ahead anti-clockwise than the other one. So if you're drawing it like this, then this one leads. Whatever is on this axis leads, this axis leads, this axis lags. If you draw it like this axis leads, this axis lags. But another thing you should look at is the value. Once you draw like this, it means this one is a negative, this one is a positive, this one is a positive, this one is a positive. Anyone that goes like this is a negative. You get? So you still respect the Cartesian coordinates in the vector diagram you're doing. So you know that the voltage leads because of the inductor. That's the first thing. Then since the options are looking in this way, that the voltage in two aspects, the voltage of the inductor, the voltage across the inductor should lead, then the voltage across the resistor and the current should be in line, and they should be following suit, they should lag. So it means that you have something like this. If it was something like this, then this should be your VL, voltage across the inductor, then this will be your VR, voltage across the resistor, and your current too. Then if it was like this, then this will be your voltage across the inductor, then this should be your voltage across the resistor and your current. But this is not possible because this is signifying negative value, and we know that the voltage across the resistor would not be negative. None of the voltage itself would be negative in the first place. Okay, it could be negative if it's an alternating current situation, but the voltage across the resistor alone cannot be negative. Anytime the voltage goes negative, you know that that voltage is not the one that can result to a power that can be consumed. Yeah, it cannot be a voltage across the resistor. So this is not possible. So this becomes the answer. And if you compare this to all the options, you have, okay, this is out because of the negative part. So this is the answer. Since this is having this is VL, this is VR, this is VL. So these are things that would most likely not be told to you in school. So like and hit the subscribe button, so I'll be encouraged to do more for you in particular. Thank you very much.